Hello all and welcome to a new series of videos. In this series we're looking at integration. It's a very exciting, a very useful topic. There's certainly some tediousness in this. We're going to be covering 10 exercises over the first 3 weeks of term 3. You can see here there is actually 11 exercises listed, but 11K we're not going to worry about. Integration is a partner of differentiation. It is under the broader field of calculus. I'll actually leave for now what it is, because that in itself is just a really long video. But we'll just go with, we're doing the topic of integration. It's tied to differentiation. And it's under the broader realm of calculus. So let's get going. You can see there, like I said, there's 10 exercises we're going to get through and the suggested questions you complete from the textbook. But straight away, and this might be a tiny, giving a dead set giveaway about what integration is generally used for, but we're going to look at estimating the area under a graph. Okay. Now, there's two more basic ways to estimate the area under a graph, and they're called the left endpoint estimate and the right endpoint estimate. But what it is we have some graph, in this case it's f of x is equal to 9 minus 0.1x squared as given there. And you break it into several sections. Now, how many sections you want to break it into is up to you. The more sections, the more accurate your estimate is, but the more work you need to do. In this case, we've got, or regions, we should say. In this case, we've got 6 regions that we split up into, region 1, 2, 3, 4, 5, 6. And we make these regions rectangles, because calculating the area of a rectangle is really easy. Area is equal to length times width, as it's given over here. Now, the left point estimate is about putting the rectangle where the top left corner of it is on our equation, on our line. So that point there is f of 2. And then this point here for region 2, that is f of 2.5. In each case of these, this is 0.5, 0.5, 0.5. So the width of all our regions is 0.5. As it's talking about over here at the left. This point here at the left is f of 3, then we get f of 3.5, f of 4, and then our last region we start with is f of 4.5. And each of those rectangles, if we know our function, well, we can find that height or length. In this first region, that is equal to f of 2, as it's shown here. Multiplied by the width, which is 0.5, gives us this, gives us the area of that region 1. Just the area of a rectangle using the left side of it touching the line. As we can see, though, this estimate is going to have an error. Up here, our rectangle has a little bit extra. Has a little bit extra. In this case, all of our rectangles are actually a little bit oversized, so we have a little bit of an error. But that's fine. In this case, it would still give us a rough estimate. And we'll just keep repeating this process over and over for each region. We find what the value is at the left side of the box, because that's what where the box is touching the line. Times by the width, in our case all of our widths is 0.5, and then we could add up all these 6 regions and that would give us a estimate for the total area under this graph. That was left endpoint estimate. The other one I mentioned is right endpoint estimate, which in this case we put the right hand side of our region touching our equation. So each of these touch at the right hand side. Now again, this is still a relatively good estimate. And in this case, you'll see each time the box is actually leaving out a region under the graph. So in this case, our error, we would underestimate the size of this graph. And this happens when we have a function that is decreasing, as it mentions here. As it's decreasing, because we're doing a right-hand estimate and the line is going down, our boxes, because we're always putting them touching the right hand, our box is always going to be undersized. But we could repeat this process over and over and over again, and you can see for region 1, in this case, we got 4.19, and back in our original one, we got 4.3. In our left endpoint estimate, we got 4.3 for region 1. So we can see there is a difference between the two. Either of them are valid ways to estimate the area under a graph, though. In general, when we want to think about what the areas are, if we have an increasing function, so the line is going up, if we do a left endpoint estimate, as the line goes up, so this would be left endpoint, the endpoints of our regions are on the left, we can clearly see that we're underestimating. But if the lines are going up and we do a right endpoint estimate, the right side of each of our region is touching. So as we can see, we have excess, so our estimate will be larger than the actual area, and then this flips for a decreasing function. When we have left point here, we've got an excess, and then if we did a right point, like that, clearly our estimate is going to be less than. As it says here, either method can be used to find the area under the curve. The function is not limited to only increasing or decreasing. You could do this on a curve that's like that. You just have to be careful with drawing in. If you decide to do, say in this case, left, you have to do left for the whole way. Left matching. So you can see at some points it'll be overestimating, at some points it'll be underestimating. But you can use it on a not just purely increasing or purely decreasing. And the smaller we make our rectangles, the more accurate will be the estimate, because if I halve that rectangle, I've now picked up this area. Same here, if I halve this rectangle here, I've picked up this area, and I'm getting a more accurate result. So, quick work example. The graph of the function find by the rule f of x is equal to e of x is shown. Give your answers correct to 2 decimal places, so we're not doing exact answers. Use the left endpoint rectangle method with rectangles width 0.5 to estimate the area between the curve and the x-axis from 0 to x equals 2.5. So we've got already the function drawn out here. It's y equal e to x, goes through 0, 1, and we've got in our regions, as we can see, we've got region 1, 2, 3, 4, 5. And we've drawn these as left endpoint as required. Touches on the left, touches on the left, touches on the left, touches on the left, touches on the left. Now let's just do area of rectangle 1 first, or region 1. So area of region 1 is equal to length times width. And our length is going to be the distance up and the width across. So I'll just put the width in, which is 0.5, and the length is, well, how high it is, which in this case it's nice and easy, we can read off the graph as 1, so that is equal to 0.5. Let's go into area of region 2 is equal to length times width is equal to, and we've got 0.5, but how high is that point there? And that is, we have x is equal to 0.5, so the height of that will be f of 0.5, or is equal to e to the 0.5, and I've got my calculator here ready to go. If I go keyboard, e to the 0.5, that gives me, oh, I need to go to decimal, 1.6. We'll write these first to 3 decimal places, and then we can round at the very end. So 1.649 we got as the height of that point there. And we just keep repeating this process over and over. So area of region 3 is equal to f of, and in this case the x-coordinate is 1 by 0.5. Area of region 4 is equal to f of 1.5 by 0.5, and area of region 5 is equal to f of 2 by 0.5. that's where each of those heights or lengths come out at. So they happen to be, and in this case it's quite easy to just type it into your CAS, but it would be helpful if this was a complex or more involved function. You would define it first in your calculator to make it much quicker, but E of 1 is going to be 2.718, 5.5, when I forgot to calculate the actual area, so let's put in 0.5 there, so that back here in area region 2, that gives me 0.824. Area region 3 is going to be e to the 1 times by 0.5. That gives me 1.359. And I'm just going to repeat that over 1.5. Oh, no. 1.5, 2.241, 2.241, and region 5 was e to the 2 is 3.694, 3.694. So area total is equal to all of those added together, which happens to be 0.5 plus 0.824 plus 1.359 plus 2.241 plus 3.694 equals 8.618. 8.618, so it's roughly equal to 8.62 square units, because we aren't given measurements, so we don't know if this is centimeters squared or anything, it's just square units. Right, so that's doing that using left estimate. I'll leave this as a chance for you to do a right estimate. The key thing to note is your rectangles, your width is still 0.5, but your length is the height or your x value at the right hand side. So we're not even going to use the height here at x equals 0. We have to start with using it at the right hand side. So you're going to have to use it x equals 0.5 at 1, at 1.5, at 2, and 2.5, and get your estimate from that. But yeah, that's the two methods to estimate the area under a curve. Now, what if we don't want to estimate, or what's the talk, or what's the sort of vocabulary that we use for not estimating? Well, when we're not estimating, what we're actually finding is the definite integral. Okay, so the definite integral, and this symbol in here, let me put a red circle around it. That's the integral symbol. It's sort of like an S, but it's much more sort of upright. And we have these will be numbers, A and B will be numbers, and then we're finding it of some function f of x, and then we have this dx here, and this is also a hint leading towards, we've seen dx before in differentiation, so this has clearly got something similar to differentiation. But for now, we're just going to stick with the definite integral of ab f of x dx is the exact sign, and I'll explain later more to what the sign means, but is the exact signed area under the curve of fx between two endpoints, or they're also called terminals, A and B. Okay. So in this case, if I had some graph that, let's just keep it like that for now, and I have that point A and that point B, this notation here is saying, and it'll give me some number, we want to try and find some number, and it might be 5, that all of this is equal to 5 is saying that the area under this curve, f of x, between the points A and B, this integral means area, yeah, sort of, but we'll just take it for now, this whole thing means area, is 5. We normally write the left-hand endpoint as A, and then the right-hand endpoint as B. So whatever's furthest to the left, we put at the bottom of this integral sign, and whatever's to the right, we put at the top. Well, that's all we're just going to leave for now, and how we can actually find it for more complex functions. But in exercise 11A, all it is just that when you see this symbol, that means don't estimate. You need to actually find the exact area, and we're just going to start with functions that have straight lines, so it's nice and easy. So areas under straight lines are essentially going to make triangles or trapeziums. So that's, if you know how to find the area of a triangle, which area of a triangle is equal to half base times height, and area of a trapezium is, if I remember correctly, half of A plus B times by height, where we have, let's draw it this way, that's A, that's B, and the distance between them is H. So we can just use those two for under straight lines. So evaluate the area under 2x plus 1, that's the f of x bit there, which we can see is drawn for us nicely here, between the values x equals 1 and x equals 2. So I'm trying to find this area here that's marked as shaded. Well, we need to know what the coordinate of that point is and the coordinate of that point is, because we need to be able to find these lengths here. That's our lengths A and B. So the x is clearly 1 and the x is clearly 2, so we're just going to go f of 1 is equal to 2 by 1 plus 1, because f of x is equal to 2x plus 1. Is equal to 3, and f of 2 is equal to 2 by 2 plus 1. And I apologise if you can hear my washing machine in the background. 2 by 2 is 4 plus 1 is 5. So we have those points there. That is 3 and that is 5. So clearly the length there is 3, the length there is 5. And what is my height? The distance between them is 1. So the area of the trapezium is equal to half 3 plus 5 times by 1 is equal to half by 8 times by 1 is equal to 4, and we aren't given any measurements, so we'll just say square units. And that's our area, which is, that's what that's asked for, the exact area. That's it for this exercise. Fairly straightforward. We have two methods for estimating, left bound and right bound, and then we have this symbology now introducing, which means what is technically called the definite integral. When we have these two numbers next to this weird symbol, we're trying to find the exact area between those 2 points. If you have any questions, as always, feel free to ask in class, send an email, put in the comments below, or put something on Google Classroom. Thanks and have a good evening.